So today we start the last part of the course, the last third, and this is on the physical evidence that's left behind. And so we're going to be looking not just at the chemical, there'll still be some chemistry in it because it's a chemistry class, but we're going to be looking at the physical properties of evidence. And so one of those is gunshot residue. Now you might say, well, gunshot residue is chemical. You're looking for elements, but you're also looking at the shape and sizes of the particles. So that's an important part of the identification of gunshot residue. So we're looking at the physical properties. And so that's what makes it a physical evidence piece. And so here are some common cartridge sizes for ammunition. And I brought some of these from my own personal ammo stash. So I've got some shotgun shells in here too. And so you can look at these. This little one is a 380. I'll hold them up to the camera too so you can see them up close when you go back to look at the video. So this is a 380. You can see that it's not very big. It's a little bit smaller than the first knuckle of my thumb. I use my thumb as a measurement of everything. It's about 1 inch across. Then this is a 40 caliber. You can see that on this list here, the 40 Smith & Wesson. It doesn't mean that you have to only shoot it in a Smith & Wesson. It's just that's the group that came up with this round. And so that's a little bit larger than the 380. It's almost the full knuckle. So here's the 380 and the 40. And so the caliber is not the length of the cartridge or the bullet, it's the diameter. And so the 380 is 0.38 inches in diameter, and the 40 is 0.4 inches in diameter. This one's a 40 also, but notice the ends are different. And so this one with the little red plastic piece in it is a hollow point, and the red plastic part helps it expand. And then this is a full metal jacket, so the lead bullet is completely enclosed in a copper jacket. So you hear that's sometimes abbreviated to FMJ. This is a 22 long rifle, also about the same length as a 380 cartridge. Okay, but the diameter is 0.22 inches. And this one is a little dot in the middle. You can kind of see that it's a hollow point, 22 long rifle. And I'll put these back in the baggie and show you, pass them around. This is a 223 cartridge. You can see it right here. It's the one in this blue box here. And so for scale, it says almost as long as my thumb here. Okay, and it's 0.223. So the bullet size, the diameter of the bullet is about the same as a 22 long rifle. Okay, but look at the different size cartridge. So this has a lot more powder in the cartridge, and therefore it goes at a higher velocity. Now, do you remember from physics what the kinetic energy equation is? Go way back to physics. Throwing a baseball, right? I hear some mumbling, yes? Yeah, so kinetic energy is equal to, I heard some mumbling, say it again. 1/2 m for the mass and velocity squared. Velocity squared. So the energy of this bullet coming out of this cartridge is enormous because of the velocity. Okay, so that's what these high-powered rounds, these would be called high-powered rifle rounds with the more powder. So that cartridge is necked out to hold the powder. And so more powder means more burning, more acceleration, more velocity, more energy. And so this is the round that everybody, the AR, the scary AR, that's that round. This is a 30, let's see which one did I bring. This is a 270. So the diameter of that bullet's 0.27 inches, but look how much larger it is. So this is a deer rifle round, and it has a lot more length, a lot more distance that you can get. It doesn't fall off. Since it's going so much faster, it doesn't fall off. So you can shoot further, easily 300 yards. I can't shoot 300 yards, but because I don't have the scope. I haven't spent the money on optics. Okay, so those are the rounds there. And then these are shotgun shells. And so they're filled with a bunch of little BBs, the different size. This is a number 8 or size pellet. And so The powder's in the bottom. You can kind of see some white, the bottom part is not as dark as the top part. The top part's dark because inside this plastic shell is the shot. So it's a bunch of little BBs. Then you have a wad, a little plastic wad that pushes the shot through the barrel, and then you have the powder in the bottom. And then all of these rounds, except for the 22 long rifle, have a primer in the bottom. So the primer is where you have the lead stiffnate. Okay, that's a shock sensitive propellant. So you strike the primer with the firing pin, and it starts that lead stiffnate to burning. There's a tiny gasket between the primer and the powder, and that gasket bursts when it reaches a high enough pressure and temperature, and then it goes into the powder and catches it on fire. It is not an explosion or a detonation, it's a burning. So the powder burns at a well-characterized rate and pushes the bullet, accelerates the bullet and pushes it through the barrel. Now the barrels are rifled, meaning they have some twisted ridges in them to spin the bullet. And so that allows the bullet to maintain its direction. So just like the bicycle and the angular momentum of the wheels, it's easier to balance once you're moving. Same thing, you don't want to tip over because of the angular momentum of the wheels. Same thing with the bullet. As it's spinning, it's more resistant to wind being pushed around or tumbling. It's spinning, so it maintains its aerodynamic nature and can go a long distance. So I'll put these in the baggie and pass them around. You can look at the backs of the bullets to see what their calibers are. And then here's some bullets that actually bounced off of our target. Don't take them out of the bag because they're lead, but you can see the back side of the bullet here, and you might be able to see the rifling. And so that would be something that you could use in a ballistics examination. You have this round that may be recovered from a victim or the place of the crime, and then you shoot a round out of the suspect's gun, and you compare the ridges in the barrel. And that would show that this bullet came from the same weapon. Okay, you might be able to catch the primers. So these are shotgun primers. A friend of mine reloads, and he had a bag of these, and so I grabbed a bag. I said, "Can I take this to class?" And he said, "Yeah." And so that's way too many. But you can see this is all the spent primers in his shotgun shells. Now, these are just trash. When you're reloading, you throw these away. But if you can look here, you can see all of the little divots that the firing pin made. And some weapons have a slight deformity in the firing pin, and you can track them using the firing pin impressions. So I'll pass these around. You can have fun looking at them. I'm going to tap over here. And some of you may have experience with different, shooting. Well, let me put this in the bag so we don't have 40,000. I need to get campus police involved so they can come and we can disassemble a pistol up here and you can see all the parts. But I just never think of calling them until it's today, You've heard of the AK-47 or whatever, the AK platform here, the 2 rounds of those here in the middle. And then different deer rifles. You might have heard of 30-06 deer rifle. That's this one. The 270 is very similar to that one, the one that I have in the bag. Either that one or this one, the 303, in terms of size. And then this is, look at this, this is not to scale. The 50 Barrett machine gun, the 50 BMG, is huge. It's probably that long. Okay, $2 or $3 a shot. So if you get a chance to shoot one of those, you're in for it. It kicks. Okay, so these are just all the different ammunitions and cartridge sizes. Okay, these are the parts. So here's the primer. This has been cut open just to show you what was all made. So here's the primer here. The primer goes into this little slot in the cartridge or the casing. You see that little hole there? That's where the hot gases go from the primer to the powder. This is the powder. It goes in there. And then the bullet is just wedged in to this opening. And this one is a hollow point. So inside you have lead and typically copper on the outside. The casing is typically brass. Although there's a couple that are in the bag that are stainless steel. This is now we're pretty much all converted over to smokeless powder. Where they've added a little bit of some nitrated like cellulose and so on, some explosives, but small amounts, so that it burns completely. So because of the complete burn, it doesn't push a lot of smoke. And then this is the primer. So the primer and the smokeless powder have, the primer has some lead in it. And then the smokeless powder has some bismuth, or some barium, I would say, barium and antimony sulfides. So they provide some sulfur that helps with the burn, but then they leave behind this barium, this antimony, and this lead. And so we'll see that those are some indications of gunshot residue. So here are the top 20 gun types seized by Chicago. This was a graphic I found online. Some of the more popular ones are these. All of the Glock ones are very popular. This is a 45. Down here is a 9mm. The subcompact. The subcompact are essentially pocket guns. And they're the most, for concealed carry, they're the most concealable, okay, because they're the smallest. The thing you sacrifice in that is you don't have a lot of rounds in the magazine, and so there's not much that you can do, but you can protect yourself, okay. These revolvers, those are the least expensive, and so they're very popular in terms of people buying an everyday carry gun. Let's see, I don't know what else to say about that. Now here's the different shotguns and rifles. You have different types of shotguns. A cute little cartoon I found online. Again, this is a break action. You break the gun breaks in the middle here, and you can put the shells right into the barrel. And so you put the shells in the barrel, you click it closed. This happens to be a double barrel, so you've got two barrels here, so you can shoot two shots. This one is a semi-automatic, where you would probably have either some sort of tube magazine where it loads itself. Again, most of these will have a plug in them because for bird hunting, there's a restriction to 2 shells in the magazine and a third in the chamber, so you could shoot a maximum of 3 times. Most of them will hold 5 shells. For home defense, typically they're fully loaded, but a lot of times people don't take the plugs out, and so they only have 3-round capacity. And then the pump action, it's not semi-automatic. When you pull the trigger, you have to pump this this lever, I guess, and it ejects the old shell and loads a fresh one. This AK format is really inexpensive to produce, and so that's why there's so many thousands or millions of these across the world. This lower receiver here is essentially made out of sheet metal. And that's why it's so inexpensive to make and pretty robust. It's hard to believe how much punishment that particular type of rifle can take. Mud, grit and everything, and it will still shoot. These deer rifles, bolt action, so these are the ones like you see the 270, that really large shell. This is what that rifle looks like. And then you have the semi-automatics. The AK is semi-automatic. A military version can be made into a fully automatic. And then this is the AR family. It does not stand for assault rifle. It stands for Armalite. Okay, and it's become popular because it's like the Legos of firearms, because you can exchange the barrel. You have this nice little rail on top. You can put a little bipod. You can put a little handle. You can put all these different things on it. You can put a scope. You can put night vision, flashlights. You know, like I said, it's for the tinkerer. They love to outfit them with all kinds of accessories. You can buy large capacity magazines, and you see there's a legislation to try to restrict that. It's pretty typical to have a 30-round magazine. It's another nice thing about the Armalite family that's different than these high-powered rifles up here is notice that this is all solid. The only cushion you have is these little bumper pads. Cushion. How do you spell cushion? Okay, so when you shoot a deer rifle, you take some punishment. Okay, now you don't necessarily feel it when you're hunting because you're excited, you know, and you shoot, you know, you're not paying attention to how much it kicks. But if you're out shooting targets, after a while, you're like, okay, I think I'm done, because it just beats your shoulder to death. But this has a buffer tube in it. And this is what makes another reason why these are so popular. And so when this fires, this upper assembly slides back into the buffer tube, and there's a spring in here. So that slides back, throws out the shell, loads another one, and is ready to fire again. But that spring absorbs all of the shock. And so you could shoot an AR rifle for fun, shooting targets or whatever, and you don't feel anything. It doesn't hurt. Yes. Oh, I'm sorry. Yes. Mm-hmm. Okay, so let's. So why would you saw off a shot? First of all, they're illegal if you make them less than 16 inches. Okay. Yes. Why? Well, there's that, and also it just makes it smaller, right? So you saw it off here, and then some people saw off the stock too. And so that would be typically someone would do that for home defense, you know. So it's it's just a pistol, boom, and it's a point in the general direction type weapon. It's not going to be good for bird hunting. It spreads out the shot, but for close range in the house with an intruder, with your eyes closed, bang, you know, it's gonna do some damage, and they're gonna run. Yeah. But that's typically why somebody would do that. But again, the regulations restrict a lot of those kinds of modifications. And so as soon as you do that, then you're in possession of a short-barreled rifle, and then that ATF could knock on your door and come in somehow. Like if you're stupid enough to post on Facebook, you know, made some mods, you know, check it out, and they're like, oh, how about that? Let's go make a visit. So how do you regulate this? And this is the tricky thing, especially with all these accessories. And so the National Firearms Act has all kinds of rules written about lengths of barrels and this and that. And so what actually is a gun? They had to define what a gun is. And so the lower receiver is actually the gun. So this right here is classified as the gun. It's really kind of strange. It doesn't have any bullets in it. In fact, without the magazine, it can't do anything. Without the barrel, it can't do anything. So it doesn't even have a barrel. It doesn't even have a firing pin. This thing that I've circled cannot fire a bullet, but it has the trigger and it has the hammer. Okay, and so they decided, okay, let's make the lower receiver the gun. Okay, so that's the definition of a gun. And you now have online, I mean, it's a pretty scary time we have. You can print this out of plastic. So there's plans to 3D print lower receivers. Now, is that legal? Yes, in this country, you have the ability to make your own firearms. It's not that you just have the right to possess and bear arms, but you can actually make them. So you can make this lower receiver, You can't make it for the intention of selling it, okay? But you can make it for your personal use, okay? Now, if you do that, then it wasn't manufactured at a manufacturing facility and it has no serial number. So because it doesn't have a serial number, it can't be tracked very easily. There may be other ways to track it once it's used in a crime, but off the 3D printer, you can't track it. And so that's what they call ghost guns. So when you hear that term ghost gun, there's nothing radically different about a ghost gun. A ghost gun is a gun that does not have a serial number. Okay. Now they've expanded that definition to guns that have had their serial numbers obliterated, which is a new thing, and I think they did that. My opinion is that they expanded that definition to contain the group of weapons where the serial number was scraped off, to increase the number of ghost guns that are out there. So they could say, "Wow, look at this problem." There's really no way to know how many ghost guns are out there. But if anytime a police department seizes a weapon that has had the serial number scratched off, I think that now goes into the category of a ghost gun. When in the past it did not. Okay. Good question though. Any other questions? Yes. Okay. So these are the constituents in the primer and gunpowder. The three primer elements are lead, barium, and antimony. So we actually get to use that elemental symbol SB. So stibnium. But we call it antimony, and it's from the oxidant barium nitrate and antimony sulfide was a fuel. Then the gunpowder has nitrocellulose and nitroglycerin blended in so that you get a complete burn and a more accurate measurement of how much energy you're delivering to the bullet. The minor components that we can detect pretty easily using swabs and so on are these stabilizers like diphenylamine, ethyl centralite, methyl centralite, hydroquinone, and resorcinol. These are all sort of aromatic free radical scavengers or antioxidants. Why do we want those? Well, we have a pretty reactive mix. We've got nitrates, sulfides, you've got oxidant and fuel right there. And so you don't want the ammunition to just get old and stale, right? So we put in these antioxidants. So if the nitrate starts to oxidize something, it's going to oxidize the diphenylamine first before it oxidizes the sulfide. And so that will keep the ammunition fresh. So, okay. And so here's a picture of firing a revolver. It's a friend of mine, and she posted this picture, and I was like, "Can I take that picture and use it in my class?" And she said, "Yeah, sure, whatever." So you can see revolvers are some of the dirtiest guns to fire because they have that break between where the cartridge is and the barrel. And so a lot of the gas escapes through that gap. Most of it goes out the barrel, but some of it escapes out the sides and it covers your hands and forearm and so on. So I don't know if you can see it, but this cloud goes all the way back here. I'll trace the cloud in case you can't really see it. So this smoky cloud, goes almost to her elbow. And so she's going to have gunshot residue all over her arms. And that would say that she was in the vicinity of firing a weapon. You can't say that she was the one that fired it. And so that's one of our Kahoot questions if we have time to get to the Kahoot. So where would we collect the gunshot residue? Of course, you want to go where the densest amount of material is. And so typically on the top of the hand, because it's going to blow back and settle on the hand. Now, your hand is pretty sticky to these particles. One, they're really small particles, and two, your skin is moist. Okay, and so it's just going to be like a glue trap. So those particles are going to land on your skin. You got to come along and swab them off. Okay, so this is a fantastic picture. You can see from that revolver some of the fire and smoke escaping between the cylinder and the barrel. But again, most of the fiery particles going out the barrel. And this is a cool picture because we actually got the bullet exiting. So here's the bullet right there. That's really fantastic. And then all of these streaks, that's the hot metal that's forming little spherical, irregular spherical particles as they blow through the air. And so these hot streaks are metallic particles. The reason they're bright is because they're hot. So it's that black body radiation. It's emitting light as it cools down. And they're flying all over the place and landing on clothing and on hands. Now, most of them go forward. And so if you have a close range shot, you'll see charring and particles embedded into the clothing of the person that got shot. So you can come along and you can swab with these little kits. So this is a little swab kit, and you swab the hand. You got a little thing that says right hand, left hand, case number, subject, and all of that. And some people, they say they can swab the face, the hair, the clothing, and so on. Here's the charring from close range shot. That is a very close range shot. So there's a lot of the hot gases burn the clothing when it hit. So we can use color tests, like that charred spot with a hole in it. I mean, it looks pretty obvious that that's gunshot residue, but we could still do a color test. There's a couple of color tests: the modified grease test, which tests for nitrites, and the sodium rhodizonate test for lead. Okay. And then we can use instrumental analysis. If we get the particles, we can do an SEM. I mean, this is a pretty exotic. I don't know when they would use this. Maybe in shooting the president or something like that. But neutron activation and analysis is extremely rare. You'd have to go to a national lab to get that done. You're never going to come across that in a run-of-the-mill forensic facility. But anyway, you can shine neutrons at elements, and it activate the nucleus, and then those nuclei emit gamma rays, and it tells you what element on the periodic table you have. And so it's much more common to have X-ray analysis from scanning electron microscopy, and so we'll look at that. So let's look at these color tests first. You take the photographic paper, which you guys have probably never seen, being in the digital age. Back in the day, you used to have photographs. Maybe you've seen the Polaroids. You pull the Polaroid out, pull the paper, wave it in the air, and that photographic emulsion, you put that on there, and you can place the questions side down with a gelatin-coated photographic paper on it, and put a cheesecloth with acetic acid on it, and press it with a hot iron, and then you peel it off, and the orange color indicates nitrite residue. So here's a picture of that photographic plate. So it was pressed on the question object, like clothing. You press it on there, it pulls the particles off, and then you get a color change, and you take a picture. You say, yep, we see gunshot residue. Sodium rhodizonate. Look at rhodizonate. That's just a cool molecule. That is one heck of an oxidized ring, man. Need to do the symmetry of that one next time at PChem. That would be great. As it stands right now, this is a C2V molecule, but still, if you could delocalize those negative charges, you might be able to make it a D6H. But that's inorganic, so we won't go there. Okay, so then we could spray, we could test for the lead by spraying the question surface with this sodium rhodizonate, spray it again with tartaric acid and sodium bitartrate buffer solution, then spray it with hydrochloric acid solution, and then you'll get the pink color, and then it'll fade out, and blue violet will show up. And so here's the sodium rhodizonate test. You see that violet color develop. You got the hole there, and you see the gunshot residue giving you the color change. Not going to work on a really dark garment, but maybe you can pull some of that off with cheesecloth and test the cheesecloth. So here's some pictures of tests given from Joe Trevino. He was a SAM grad from 2013. Went and got his master's at Pace University in Manhattan. So he was looking at programs. He'd originally wanted to come here, but then he started thinking, well, why do I necessarily want to restrict my target for forensic masters to SAM only? And he looked around, and he found a school in Manhattan, Pace University, and they had a master's in forensic science. And so he went up there. So, if that interests you, I can put you in contact with Joe, and he can tell you about his experience. And so pretty neat. So he said that when they're told to send something off for gunpowder analysis, they're really talking about trying to track the muzzle to target distance. And so that's when they're testing the targeted clothing, and trying to figure out the ammunition that was used. Okay. And so here's a picture of that pink color, and then it turns to purple. So that was the rhodizonate test. And so it starts out pink, and then you add the hydrochloric acid, and it turns to blue violet. So this taking photographs, of course, is non-destructive, but some of these chemical tests, if you're spraying all these chemicals on the garment, you're changing the garment. So we would call that a destructive test. Swabs are non-destructive, but you're collecting the evidence and then sending it off for analysis. So here's some different kinds of swabs. You've got the little Q-tip, which would be great, but they make these little plastic holders that go over the end of the Q-tip. So you swab the hands, swab the clothing, pull it into the plastic deal, close the cap, and break off the stick. And so then you've got the evidence right here. Put it in the box or label it with tape. Here, I like this one, the little foam dauber. So you pull this off, daub the hands, put the little cap back on, tape it up right on the tape, and send it off. And the penny's in there just to show you the size of it. And then we send it to a facility that has a scanning electron microscope. So not every lab's going to have one of these. Our police department here does not have those. Our police department could collect gunshot residue, but they're not going to be able to analyze it with an SEM EDX. They cost $200,000 to $400,000, but the real cost is the maintenance contract on that, which would be it's about 10 to 20% of the price. So 10% of the price would be $20,000 to $40,000 a year. 20% of that would be $40,000 to $80,000 a year. And that's quite expensive. And that's just the equipment. Who's going to run it? And so then you're going to have an analyst that's trained on it, that can maintain it. And so you really need a person. And so the cost is, yeah, the instrument's expensive, but the person is also expensive. The labor costs are really your largest expense. So this is, again, how the electron optics in an SEM work. What is an electron gun? It's just a hot wire, high voltage. So you've got tons of electrons trying to go through a wire. And if you give them another path to ground, they may take it. And so you've got, so the electrons boil off of this wire. Then you can use electric fields to focus that and drive it onto the sample. Now, let me show the raster pattern. Raster pattern. So with these electron optics, these deflection coils, you can do this with the electron beam. You can go on like a stripe and then start again and do a stripe. So you go left to right and then start again and go left to right again and then start again and go left to right. So that's what we mean by rastering. So you're going over the whole image very quickly with this electron beam. And how does that give you an image? Well, you're keeping track of every spot on here. So at spot number 1, you look at the secondary electrons that are generated. So you're shooting electrons at the surface and they're bouncing off. Why would they bounce off? Because everything has electrons. And so they get close to the surface and they scare off electrons from the surface, or they themselves splash off the surface. Okay. It would be interesting to do this like physically if we had like a high power, say, pressure washer. Okay. And I don't know, I'm thinking in my head, like if you could spray from the ceiling everything in here with a pressure washer, and you had a detector over here, like your face, okay? And on some angles, you would get a lot of water splashing in your face, and in other places, you would not get any water splashing in your face. And so as you raster through here, your face would feel more or less water, and that's the brightness of the image. And so we just take the electrons splashing on this detector from this beam, and we get an image. If we keep track of where we were shooting when, with each detection, then we can get an image. So that's how it's produced. There are secondary electrons produced. So this E-beam comes in and can scare off or splash off these electrons. Some of those electrons will be in the 1s orbit. If we knock an electron out of a 1s orbit, then we get X-rays as those outer electrons jump in to the open chair. Why do they want to do that? Well, this is the nucleus, so this is incredibly positive. So these are the lowest energy electrons that are really close to the nucleus. So when an outer electron jumps close to the nucleus, it releases enough energy that it's in the X-ray region. That's how much energy is released. And so we can use this to characterize the elements. So we would look for lead, barium, and antimony, and they would be spheroid. So they're rounded but not perfect spheres. So this is where training and judgment comes in. How imperfect is the particle? It should be a molten sphere, but it doesn't have to be perfectly spherical. Okay? If it's perfectly spherical, that's kind of suspect. And if it's not molten, that's suspect. So I've added a few extra images this morning to kind of show you some other things. So particles containing only 2 of those 3 elements are described as commonly associated with GSR or consistent with GSR or indicative of GSR. But if you have all 3, then you could say it's confirmatory of GSR. So here's pollen grains. So notice the GSR, it's really 0.5 to 50. I looked it up. I have in your notes 1 to, what I say, 1 to 10. But it can go a little larger than that, to 50 microns in size. So half to 50 microns in size. Well, SEM pollen grains are right in that range, 2 to 25 microns. So whenever you're looking at a sample, you're probably going to find pollen. Where was my friend? She was outdoors. She was shooting her gun outdoors. So she probably has pollen all over her hands too. Okay. So this is what pollen looks like. It's the correct size and they're round, but they're not molten. How do I know they're not molten? Have you ever thought of it? I mean, look at these particles. Do they look like they've been melted to you? They're perfectly round. There's some strange ones, like this one's a little weird, right? And these have some little divots in them. And here's a triangular one. But yeah, the perfectly round ones, like this one is perfectly round. But I know this particle has not been melted. Why? Huh? The pokes, the spikes. Think about a snowflake. What happens to the beautiful spiky part of a snowflake when it melts? They leave, right? You can't have those fine features when you heat it up. It's gonna melt, and those fine features are gonna disappear. So whenever you see surface structure like that, you know it's not been molten. Okay, and it's so perfectly symmetrical and regular. So you should be able, and again, that's a physical property, not a chemical property. You're looking at the physical shapes of those little spikes. You know that that's not been melted. Okay, and they're not really irregular in the way that we would think of gunshot residue. This is a new picture. This is sand grains. Okay, so yes, they are irregular shapes, but they're not round and they're not molten. Again, we don't have those spikes, but we do have sort of sharp ridges, and those sharp ridges would soften if these were melted. They're definitely not round. These have been sheared and cracked and broken, not melted. And look here, if you don't have a size indicator on your image, as a microscopist, you've failed, right? Because we got to know what is the scale of this image. And this is 500 microns. So this is too large. This is 500 microns. So this one is about, 200. So these are all too big. These are beyond the 50 micron range of gunshot residue. Now here, this is gunshot residue. So you see it's 1 to 50 microns. I don't have scale markers on here. So whoever I got this image from online or in Pearson's book, they've let us down. But trust me, it's the right size because this is gunshot residue. Notice how rounded it is, and it's molten. And some of these have like cavities in them. See, that's interesting, these cavities. This is a little weird. This one's not quite round. It's rounded, but it's not round. This one looks like it has spikes, but those are irregular bumps. So, I would I don't think that you could mistakenly call that pollen, because it's not. Those little bumps are not perfectly, spiky and symmetrical. Um, but the real test, once we get what we think is a suspected gunshot residue particle, is we stop the rastering, because the rastering is splashing a small amount of electrons across the whole image, and we target the particle. So we would send an electron beam. We might select it with the mouse like this, and we would say, okay, blast the crap out of that particle and tell me what chemicals are in it. And so it starts sending all of the electron beam at that particle, so that the probability of knocking out the 1s electrons goes up. So again, there's a certain probability we'll knock out a 1s electron. You send more electrons on the particle, that probability goes up, your signal goes up, and then you get this image here, the scanning electron microscope, EDX, so energy dispersive X-rays. So we take the X-rays that come out of that, send them off a glancing angle of a monochromator, and disperse the energy of those photons and detect them with a liquid nitrogen cooled X-ray detector, and we get this spectrum, and you can see all three of the particles, the correct chemical composition. So we see lead, antimony, and barium. Notice this gets some oxygen here, but then it cuts off at oxygen. So you see up there, oxygen is this sort of the smallest element we're going to test. So we're not going to do an SEM on an organic substance and capture the EDX scan of the organic substance. In fact, there's typically so much carbon in the system that it would just overwhelm the detector. So we just block that part right below oxygen and look at the metals, all the heavier elements. Okay, and you can see chlorines too. I guess it doesn't have to be metals, but I mean, look at the periodic table on the second row down. It's mostly metals. Okay, so this, again, this is important. The presence of gunshot residue can't determine whether the victim's death was a result of homicide or suicide. They won't even run the sample to try to make that determination, because, let's say the person's dead in the vehicle. There's gunshot residue on them. There's gunshot residue on everybody in the car. So you couldn't say whether it was homicide or suicide. It just says that everybody in the car was there when the gun went off. And so they won't even run the sample to try to make that determination. As Joe was saying, it's more times than not they test the distance to the victim if they're going to run gunshot residue, and try to get sort of the cone to measure how far away the weapon was. So if it's positive, we just say that it's consistent with that person's having fired the weapon, or having been in the vicinity of the fired weapon, or having touched an item with gunshot residue on it. If it's negative, it doesn't necessarily mean you weren't in the vicinity. You could have false negatives, things like hand washing. Maybe it's a raining situation and everything is drenched with water and you just didn't detect the gunshot residue. It could be some sort of wonky formulation that changes the components of the ammunition. You could just be covered in mud and grit and grime, and so you just lose those gunshot residue particles in the background of all this other stuff. And so that's, there are some chances of false negatives. Some ammunitions are removing the antimony sulfide, and sometimes they're eliminating the lead, and so we're going to get more and more false negatives where there was gunshot residue on the person, but we didn't detect the lead or we didn't detect the antimony. Okay, and then there's other things that are not firearms that can give you gunshot residue. One of the most common would be things like this stud gun. So this thing is an interesting deal. You put these little 22 long rifle cartridges in them, but without the bullet. So these are what we call blanks. And you stick them here, and you load a nail in the other end. And you can put this on the stud and punch the button, and it drives the nail through the stud and into the concrete. And so it's such a rapid pulse that the iron of the nail can drive into the concrete and fix the stud down to the concrete base. Yes.
Sorry, does it kind of work the same as like a cattle prod, like an air gun?
Well, it's in a sense, it's the burning propellant that's driving the hammer into the nail. Okay, so in that sense, it's air, but it's a lot higher pressure, I would say. Yeah. So what's the cattle prod air part? What are they? I thought a cattle prod was electric, like a taser.
Oh, sorry, I got the word wrong. That is a cattle prod. The thing I'm talking about is they would get like kind of like a nail gun in a sense, where they would just put the gun up to the cow's head.
Oh, I see. Yeah, to dispatch them as quickly as possible. Yeah. Yeah, I don't know anything about those, but it's compressed air typically. This is a rimfire cartridge, just like a .22 rifle, but it doesn't have a bullet in it, and so it's put into this high pressure. It's kind of like a barrel, okay, and at the other end there is a rod that will drive the nail. Okay, so it's like a one-shot nail gun, okay, with a little bit higher pressure than a regular nail gun. A bulk cattle gun, okay. Oh yeah, and the guy, if you ever, this would be fun just for your own curiosity. It's not related to our course at all, but go on YouTube and look up the lock-picking lawyer. Okay, the lock-picking lawyer, fantastic channel. There's not a lock that he hasn't defeated. I mean, it's amazing. People send him all these different kinds of locks and say, yeah, try this one, fancy pants, and he defeats it in no time at all. But so when could this be used when it wasn't like a crime against a person, right? They can use this against a lot of padlocks, and so the force is so violent that it could just break a padlock. And so you might have somebody that uses this, and maybe there'll be some gunshot residue on them to show that they were in fact in the presence of something like a stud gun and breaking in. So I don't know if that exotic case would actually be pursued by the police, but in theory, I could see that you would have some gunshot residue on your hands from using something like this to break a lock, and yet you didn't shoot anybody, but you maybe did a property crime. With caseloads and things, I doubt that they would do that, but you never know. Depends on what they stole, right? So let's so from the explosive detonations, we looked at some of these analyses. Again, you've got like a gas chromatograph or liquid chromatograph, and you can get all of these different compounds. So this is a fantastic chromatographic method in that it can get all of the different stabilizers. You've got an internal standard here, the toluenes, trinitrotoluene, all the dinitrotoluenes, the nitroglycerin, and this is capillary electrophoresis. Yeah. So, and then here's the plasticizer compounds that I've been talking about. So these centralites, you see, they have the dinitrogens with the carbonyl in between. The diphenylamine. Again, a lot of these can scavenge free radicals, and then the dibutyl phthalates. Now, casing materials and the detonators. Here's a picture of, or not a picture. Here's a cell phone that was destroyed with a 1/4 pound of tannerite. So I talked about tannerite. So they set a 1/4 pound of tannerite on top of this and blew up this cell phone. So that's a pretty big detonation, and you can see what's left. Here, Clifford, you want to come get this? You can see what's left of the phone, essentially. If that phone was what was used, you can pass it around. Yeah. If that phone was what was used to set off a bomb, there could still be a lot of the material left over. Okay, so let's do a Kahoot.